Hi, I'm here today in the Yellow Submarine Chamber of the ITIS Foundation in Zurich, and I'm going to show you how we do implant safety testing according to Clause 8 and Clause 15 of ISO 10974. Let's start at the beginning. Medical implants with long leads pick up energy during an MRI scan. That energy ends up at the electrodes, which dump that energy into the surrounding tissue, and at the lead terminals, creating a voltage spike which can cause a malfunction. The ISO technical specification 10974 tells you how to measure a leaded implant and tell if it's safe. Clause 8 focuses on RF-induced heating, and Clause 15 focuses on RF-induced terminal voltage. The goal of this kind of safety testing is to show that the implant is safe for every person, for every position, in every kind of MRI scanner. That's a big job, but the Tier 3 approach of ISO 10974 splits it into smaller problems that we can solve one at a time. Step 1 is to create a model of how the implant responds to fields when immersed in tissue simulating media. That's what I'll show you today. Step 2 is to scale the model and to validate it by exposing the implant to different incident fields and seeing if the prediction matches the reality. This will be the next video. Step 3 is to figure out what fields the implant will actually experience during the MRI scan inside the patient. And Step 4 is to apply those fields to the model and find the worst case. You can learn more about this from the videos by Zurich MedTech linked in the description. Let's see how Step 1 works in practice. This is our new SAMD-U validation device. It has a flexible lead with a bare tip and a shielded connector in the base, which lets you measure the voltage at the lead terminal. This implant is complex enough to have all coupling features of an AIMD, but simple enough to perform a full 3D electromagnetic simulation with small uncertainties. This allows us to derive accurate target values to be used for the validation of the measurement instrument and the procedure. The uncertainty of these can be considered to be largely independent of the complexity of the implant. We will now measure the same parameters with this device and compare it to the target values. If we find an agreement within the combined uncertainty bounds, we will consider the measurement setup and applied procedure to be validated. First, we'll make a piecewise excitation measurement of the implant with the PIEX system from Zurich MedTech. The implant is fixed on the racetrack like this. It's important to use non-conductive tape and to avoid covering the electrode tip. Use the ruler along the racetrack to make sure that the electrode tip is lined up with the E-field probe, which will measure the response at the tip. In our case, it's at 930 millimeters, so we put the electrode tip there. This is the RF over fiber probe for medical applications. We'll use it to measure the induced voltage at the implant terminal. It has a tiny broadband transducer, which is connected by optical fiber over to the remote unit. Now I plug the probe into the validation device. It has these little silicone gaskets which help to waterproof the connection. Now we can put the racetrack inside the phantom, which is filled with the tissue simulating liquid. Here we have to avoid bubbles collecting in the area of the electrode around the implant. It can help to tap on the racetrack or to put the implant in and out of the water a couple times. This is a fiber optic time domain sensing, or TDS, E-field probe. You can see that the implant is lined up with the TDS probe that measures the electric field at the tip. Don't forget to check the conductivity and temperature of the liquid. We use the portable DAX to check the conductivity at 64 or 128 MHz. The thermometer and the DAX are both traceably calibrated. The DAX is also set with an open short load calibration just before the measurement. The PIEX analyzer connects to the remote units of the E-field and voltage probes. Since it has two channels, we measure the transfer functions of the tip and the terminal voltage at the same time. The PIEX exciter is mounted on Speag's DAISY robot, which will sweep it precisely along the implant. The PIEX system is connected to the DAISY software so that the DAISY system can position the exciter at each step, and then the PIEX can automatically capture both data points. First, we run the PIEX software installed on the PIEX analyzer's computer, which will initialize the exciter and start radiating. Then we open the DAISY software to create a job with the PIEX script. We tell the DAISY the length of our device and the measurement step size. Let's use 5 millimeters today. Now we start the PIEX job we just defined, and everything will work automatically. The measurement is done in just a couple minutes. We also run a background scan so that we can subtract the exciter from the measurement. Now we can analyze and look at the results. The measurement is automatically sent from the PIEX analyzer into the DAISY software. So all we need to do is open the DAISY measurement file and then look at the data or export it into Excel or MATLAB as we prefer. We can also automate this with a Python script to extract the results automatically so we don't have to do this step every time. We can see the real and imaginary components of the measured voltage, or the magnitude and phase. The next step is to perform a background scan to subtract from the tip transfer function and plot the results versus distance. Here I've plotted the voltage results compared to our target values. As you can see, the deviation is very small, well within the combined uncertainty. That's it for today. In the next video, I'm going to show you how to scale the results and also to validate them under a range of incident field conditions. Thanks for watching.